There is a change of presenter. The next presentation will be presented by Dr. Robert Tryon, CTO of VEXTEC company. Bob is responsible for, and now you've given me a real tongue twister here, development and application of probabilistic microstructural reliability and prognostic models for the mechanical behavior of materials, including metals, ceramics, and fiber-reinforced composites. Try to say that 3 times quickly. He has published over 30 papers, including articles in accepted engineering journal publications, and holds 7 patents. He'll be talking about computational modeling of complex systems using integrated computational materials engineering. Please join me in welcoming Bob on stage.
Thank you. Well, thank you all. I guess I'm what's holding you back from having lunch. So pay attention or I'll talk a long time. So let me find what did I do with that? So I'm going to talk about mostly the field of ICME, which is Integrated Computational Materials Engineering, which many of you know about, but how that directly applies to being able to predict fatigue on a more fundamental using more fundamental models, and actually driving into what's causing fatigue damage, and how do we take everything we know about fatigue mechanisms, material microstructures, and computationally, how do you integrate that into models that predict the fatigue? So kind of with that, I'm going to go over just very briefly the traditional method, which you all know, safe, life, and damage tolerance, and how those work into a ICME-based method, which is more of a total life method. So in ICME, ideally, you're going to model the material as an initial set of discontinuities. There's no equivalent initial flaw size. You're trying to model what's fundamental in the material itself, and how does that culminate in the generation of dislocations, fatigue cracks, and so on. So kind of with that, the traditional safe life method, going way back, is we pull on a bunch of smooth round bars or notch bars. We plot those against stress, and then we find some life as a function of stress and or strain. And one of the problems is there's a lot of scatter. Even if I take a smooth round bar and I polish it the best I can, I've had graduate students sit there and do all the polishing they can just to mirror finish, I can still have huge orders of magnitude in something as simple as a smooth round bar. I can have 100, I can have 2 orders of magnitude, I can have 3 orders of magnitude in life on this, what I think is an ideally similar bar. And that's because, well, it's maybe not stress, it's not always the fundamental driver for what drives fatigue itself. So if I go back, and I'm not a fatigue guy, I had to learn this on the field. I worked for Ford and GM. They just stuck me in the fatigue group there. So I dug up my undergraduate book on fatigue, which was Professor Shigley's book. And if I look at it, and I'd like to put this up, so if I go to 188, Professor Shigley said, as an undergraduate, I need you to understand that if you find the fatigue strength of a test component, which is S sub B prime, and you want to relate that to the fatigue strength of what you're putting out in the field, well, hey, this is actually the equation he has on 188. There's all these knockdown factors. In other words, there's all these rules, and he says in the text you will learn there's very little correlation between what that bar tells you and what you're going to experience. So he says you're going to spend your life trying to figure out these Ks. And that's what every company does. So it worked at Ford and General Motors. We had different Ks. We had, basically it's our design system, our standard work design is understanding these Ks. And these Ks aren't always based on science, they're based on our experience. We had a certain failure many years ago that got a K driven to this, and now we're going to use that K, and then that person no longer works there, and I don't know where that K came from, so we're going to lose that K. So it's just a constantly rolling around to let's reinvent the Ks. And it keeps us all in business, so it's not a bad place to be. And we're going to do that, and then they keep saying, we want it lighter, we want it hotter, we want it cheaper. So then these old Ks don't work. If you want to make something lighter, I'm going to make it out of aluminum instead of steel. Okay, I got to go figure out all my Ks. So is there a better way to do this? And that's where the whole concept of the ICME comes in. So here's another thing. So why should I, when I put a notch in a bar, Why should it change the fatigue strength? Well, because the fatigue strength is not a material property. Fatigue, SN curve is not, I don't have an SN curve for steel. I got an SN curve for steel, I got an SN curve for steel with a notch in it. If I change the notch size, I got another SN curve. So we do have to get out of this thought we have that there's an SN curve or there's an endurance for a material. No, that's dependent upon all of those other Ks. Now, indeed, we've got Glinka methods, we've got Neuber methods to capture notches, but still I have to do tests. To get my parameters in those, I've got to test, and I've got to test multiple notch sizes and stuff. So it boils down to I have found ways computationally of accounting for notches and stuff by doing tests. But can I capture that scatter with tests? Because look at these, if I look at my smooth bars, ideally, there's places where I've got a lot more scatter than on my notch bars. And I understand that the notch bars got a lot less area being stressed and stuff. So I have a basic understanding of that. Can I put that in a computational form? So in other words, can I model a notch bar and a smooth bar with the same material properties and get the correct answer? So can I capture the notch? Can I capture R ratio? Can I capture even corrosion fatigue? Can things come in there? And ideally, at a mechanistic level, if I understand the mechanism, which we often do, we spend a lot of time understanding damage mechanisms, how can we work then to a computational, integrated computational framework? So, and here's another example. This is all experimental data. So I take a bar there. I've got a bar of size 1 there. That's the X. And I'm going to make a bar that's photographically scaled to half that size, and I'm going to test it. And it pretty much runs on X. And this is basically my probability or my standard normal versus my cycles. Then I take a bar that's twice that size. Okay, its life is 20% of my other bar. Well, there's a size effect that comes in. Well, how do I capture that? Okay, I've got to capture that because those little dinky bars, I'm thinking a little dinky bar, and my customer's out there flying on a 787. Well, that's a lot different size than that little bar. How do I capture all of that? So it becomes very important, especially when we're going from these very small test specimens to things like, bridges and other big things. But the flip side, going from a test specimen of a solder joint down to the solder joint that exists in a integrated package, where there's a huge difference in those sizes too, going down the other way. So how can all of these things be captured as intrinsic material properties? And so what's really going on, which is what everybody's talking about, what Professor talked about, is really there's a lot going on between when I first load that thing and that thing cracks, or I get the failure in the SN curve. And to understand that SN curve, I got to be able to model or understand what's going on. So fatigue is a process. It's not an event. It's not that I hit a 5% load drop. There's all this stuff that's going on, and can I understand what's going on to get me to that end event? And then maybe I've got a chance of capturing why those dots there are where they are. And that's the whole concept behind the total life analysis, all the work that Professor Topper has spent his life on, the work people were talking about here earlier this morning, understanding the fatigue process. And here's an example. This is, I believe this is a nickel alloy, but again, very early in life, before I've got a crack, I get things that go on such as very high strains in very, very small slip bands. So I've got a total strain, but that total strain is accommodated not by a little bit of strain everywhere, but by a whole bunch of strain in a real little place. Okay, and we all understand how intense slip and how that drives things. And those slip bands tend to stop at, grain boundaries. So, and there's a lot of models out there, Bill B., all of those guys over the years, Keith Miller and stuff, have developed models to understand using dislocation theory what's going on here. Well, how can we get that dislocation theory directly into our computational fatigue model? But the other thing that was really important that was always hard to handle is this is a random field. Okay, I look at this, and I got to handle this as a random field. And over the years, the statistical volume element methods, or representative statistical volume element methods, are out there that let me take a chunk of material and model that as a statistical volume element, such that one chunk to the next, or even in my FEA model, from one element to the next in my FEA model, I can model that as a 3D stochastic field of grains, grain boundaries, porosities. All those things are available using statistical volume methods, which have been around for a number of years, but they've become much easier to use now that computers are faster. So we actually have the computational capability to run models because we're actually going to model something like this and model 100 million grains. A piece can have 100 million grains in it. Well, if we look at it statistically, we can actually model 100 million grains because you're not modeling each grain. You're going to the tails of your distribution and actually doing models of those tails. And then here's another example. So this is a bolt hole in a longeron on an aircraft. And this would, you see there's a bunch of little dinky cracks. So aluminum 7000 series, that's how it accumulates damage. It's got a bunch of little cracks. This is going to pass inspection. This is a perfectly good hole. And I know most of you are driving home this evening, but for us that are flying home, this is what we're flying on. And they're there, and we allow them to be there, but we need to understand them to life that aircraft. And we don't infinite life airframes. They're limited life. We inspect them. They're damage tolerant, but understanding what's going on here is necessary to understand when do I need to do the inspection on that aircraft. And we can model this. If there's a whole bunch of cracks on that aircraft, billions. Can we model billions? Well, actually we can using statistical methods. And then here's another example, it's kind of from that first one. So here's a crack as it starts to get long, okay, but it still recognizes that the microstructure is there. As a matter of fact, the microstructure is going to drive the crack growth until the process zone, until the plastic zone is so big that it can average out all those microstructural inhomogeneities. But at very low loads, it might always be microstructurally driven. And the important thing is not so much that it's got this tortuous crack path, but that tortuous crack path drives the rate. So two of these cracks can have much different number of cycles to get to a certain size, a small size, because of tortuosity. One of them could take one path, one takes the other path, and as you know, driving around Detroit here, the path you take determines when you're going to get there, and that's true for these cracks also. So can we handle that? Well, using statistical volume methods, yes. Absolutely, and it's fairly straightforward. The hard part is to create the statistical volume method or the software to do it, which people have over the years, and then it becomes engineering knowledge. What rules do I need to put in there that are going to allow a crack to look like this? So that's where the computational material models come in. And these computational material models actually try to model the material at some fundamental level. So let's look at if slip's driving thing, let's look at slip. If voids are driving thing, let's populate with voids. If it's voids and slip, okay, put all of those fundamental discontinuities in the model and let damage grow from each and every one of those in this system reliability type model. So it's important that we get the randomness. Size is very important. The larger something is, in general, the lower its life is. But using this, we can go back and we can look at our test coupons. We can take data from the test coupons, not just the end life, but look at the fracture surfaces, understand where the crack started from, and we have that now. We have automated methods to put our specimens in these little RoboMet type things, and it'll go through and it'll scan the fracture surface for us and give us that. We've got a lot of methods out there that can automate this. So take that one bar that we broke, and that's a jewel. There's all kinds of data in that one bar. Look at striation spacing. You know, some of that stuff can be done now. It's much easier to do now than it was 20 years ago. And take one broken bar, but just wring all of the information out of it and make sure all of that information gets into our fatigue model. And most all of these methods are damage tolerance based. Now, they're not linear elastic fracture mechanics, but they're damage tolerance based, and that you're actually modeling on a cycle-by-cycle basis damage that builds up. And the reason they're not linear elastic fracture mechanics is what was shown in, this morning here. That could be the last 20% of life. And nickel alloy is the last 1% of life. So by the time you get to a large crack, you can be almost over with life. So if you want to capture that 80% that happens before then, you've got to use small flaw fracture mechanics, dislocation theory, crystal plasticity. But all those models are available, and you read the journals, and the journals are just full of all kinds of models available for us. How do we take that knowledge and put it directly into our fatigue modeling? So kind of the way to do that is, okay, so there's an example of a statistical volume element. So that's actually a little chunk of material. It's got, say, 500 grains in it. And those grains all have their own orientation. There could be voids in there. There could be hard inclusions in there, whatever they are. But they're statistically defined. So if I take my next chunk of material, it won't look just exactly like this, but the statistics will be the same. The mean grain size is the same. The scattering grain size is the same, as long as I'm in the same region. If I get to another region, especially in a casting, I might want to change up the statistics in my statistical volume element. But that element's available as an element, and then I've got crystal plasticity, dislocation theory models that allow me to, okay, I'm going to generate plasticity through a dislocation. I was going to say Bilby-type models, Tanaka and Mira, the stuff that Keith Miller worked on for many, many years. There's many models out there. The difference is that this crystal plasticity happens over a single grain. It hits a grain boundary. Okay, it's going to get pinched to that grain boundary, but then it's going to go on to the next grain boundary and the next grain boundary. And that happens over and over. And then there's small flaw fracture mechanics. So in a nickel alloy, you might define your initial crack as when it busts through the first grain boundary. That's your initial crack size. So you've got these very, very small cracks, but you got to use small flaw fracture mechanics to get those to grow. And finally, you get to linear elastic fracture mechanics. In some components, that's a long time. And aircraft, we design an aircraft to give us a long crack growth life because we're going to go look for cracks. So because we're going to look for them, once we find them, we've got to have some life after that. Other components, okay, we don't have any life, or we aren't going to look. So do we really care what the long crack growth life is if we're not going to use that in the safety, assuring safety? So kind of, just very, very quickly, I think it was talked about early, all of these models are based on what's going on in front of the crack tip opening displacement. So how much is that crack? What's your delta crack tip opening displacement? So closure comes into these models. Overload, if I get an overload, it's going to hold the crack down. So modeling the plasticity in front of the crack, and that plastic zone goes over multiple microstructural features. So it's the microstructure that exists in that plastic zone. And that plastic zone could vary depending upon your math. Up close to the crack, you could have one set of plasticity. Further away, you've got another set of plasticity. Finally, you get the elastic region, which sits out there. Again, there are many models for that, and what goes on in aluminum is different than what goes on in steel. Stainless steel is different than martensitic steel, but stainless steel is very close to what nickel and aluminum is, actually. But people know how that plasticity forms, and there's computational models out there that allow that. And so, kind of how that works is you can take your finite model, and at each element in your FEM, you kind of find a life for that element, and then you look at the other elements, and that can roll on. But the important thing is you get down here to the end to where you've simulated many of them. You can start to simulate what do I expect to see in a fleet of these. So if I make 1,000 of these, when do I expect the first one to fail? So that's kind of there. But the other important thing is if you're using, which you are in this room, so if you're FE safe user, can I use this to take a small amount of test data and simulate a large test program? So I'm going to go around and I'm going to bust 5 bars, but I'm going to look at them very closely, look and see what my failure mechanisms are, and then simulate those using engineering knowledge, simulate them, and then putting some more engineering knowledge. I know I can have a casting pore as big as X. Let's put 1 in there per cubic foot of this stuff and see how that drives. So things I can never test for because I can't test that many bars, I can do that and create my SN curve now, and I can create a minimum SN curve that I can use with my traditional lifing methods. So this is kind of what the output could be. Can I take a few bars, look at them very closely, and using these methods simulate a bunch of bars? And can I go and capture my -3 sigma curve or whatever I need to do, my B10, whatever is in my standard practice? Can I knock down on the number of the amount of testing I need to do to get the data to go in my standard practice? So you have to change up the entire practice to use ICME and say, okay, I'm going to do X tests, and those are going to cost me a lot of money. Well, for just a few dollars more, I can go and I can look at those much more closely, and I can get myself a much richer database, what I would think would be even a safer database to put in to my traditional standard design practice. And because this is a simulation, we're going to simulate those outputs. So now go to here. What does the fracture surface actually look like? Well, it's a simulation. You've simulated that. So the simulation output is going to tell you, okay, I've got a grain over here and it's at a real high orientation to my applied load level. It's a very strong grain, or I've got a pore over here that was in the crack path, and I can compare that back to my actual fracture surface. And this is where the V&V comes in. How do I validate? This is a pretty high level. Does my simulated fracture surface look like this? This is the crime scene. Can I match the crime scene? And if not, at this level, I can go back and I've got to tweak my analysis, but I need to match this crime scene. If my fracture surface stochastically, now not individually, but if I don't capture the proper statistics like the initial pore size where the crack started, all of those things can be captured, and I go back and I'm going to calibrate my model such that I capture this. And then I can start looking, okay, what my crack growth rates themselves. So say I was, as Professor Topper was doing, if I wanted to step up the plate and look at my actual mouth opening displacement during the growth, okay, I can go back and I'll find it's all over the place when the crack is small. Does the model show that? Is the model similar to what reality is? So kind of, with that, you can capture things like load ratio effects. There's some experimental data with some simulated data. Vibration, going from the first bend mode to the first torsion mode, it's a totally different volume of material is vibration. Therefore, you get a significant uptick in your allowable stresses in different vibratory modes. Spectral loading, this was talked about this morning, you're going to capture that because when you load it up, you got that residual plasticity and you're capturing that also. So can you capture things like spectral loading and going from simple loading to spectral loading? So kind of, and then if I've got something like a engine block, I've got different material at different locations. Okay, I need to be able to capture that too. So be able to segregate my model, but also can I go and I might have material data on one or two different flake size. Can I simulate those other flake sizes that exist in my gray cast iron? So I don't have SN curves for them, but could I use this to simulate what they would be? So kind of with that booth back there, we're VEXTec, and we're kind of in the business of developing. We've got a software that captures these models for most of the metal materials out there. So with that, I will open it to questions.
Was a very quick overview of a very complex technology there.
Yes.
Do we have any questions from the room? Must be the lunch.
Yes, it's lunch. Like, when is lunch? That's the question.
You have shown a couple of correlation graphs there. Obviously, they show very good correlation.
Mm-hmm.
How well that, you did mention that for different materials you may get different data.
Right.
Is there any feel for materials that it works better as opposed to other materials that may be a bit more challenging to characterize?
Well, over the years we've looked at a lot of different materials. I don't know that one's, of course, thermomechanical fatigue is harder to handle than regular fatigue. Corrosion fatigue is hard, so it's more of a mechanistic challenge. I don't know on a material basis. Now, castings are the microstructures, a lot more variation in a casting, so there's a lot more scatter. So sometimes they can take a more on a casting, it takes longer to get a good idea on what your variation is. If you've got an Alcoa plate of aluminum, you know what the variation is. So it's basically gathering the inputs themselves. Some materials or some manufacturing methods are more challenging than others.
And what about more advanced materials, ceramics?
And we have done ceramics. We do ceramics because they're mostly crystalline. So a crystalline material, this approach happens pretty well. We don't do polymers or elastomers.
I was going to ask
Other people do, but we don't. Yes, and we've done fiber composites. A lot of these things are based on, but the software doesn't capture those. So we look at metals.
Right.
Yes.
Okay. Any questions?
I got to ask one. We say that because of the fact we're doing crack initiation, we address a lot of those Ks that you talk about in SN analysis. And part of the reason is because we're staying in crack initiation. We're not going into the other modes of failure like propagation and so forth. Do you have any insight in that from the studies you've done?
Well, I think the Ks are still important. They're probably more important. Well, the Ks are needed for the crack initiation. I mean, propagation ideally because of because of K, because of stress intensity factors. Those have really simplified the crack growth. So we've always been much better at predicting long crack growth than we have crack initiation. I mean, the industry as a whole. Crack initiation's the hard part, and it is. We've learned what K do I need to use here, there, and the other, and how many of those can we actually? And we can still use a K approach, but can we relate those back to the K for cast iron? Notch intensity for cast iron versus stainless steel. How should those be different? But yeah, I said our whole the bane of our existence is understanding those Ks. I mean, the reason for if it wasn't for those Ks, this would be simple. But it is the Ks which make things like FE safe necessary, and for you to necessary to develop those.
Got a question here.
Yeah, so Topper talked about, you have like a high yield event. Inherently in a lot of stuff we do is formed steel. Is that something that like your software would, you have a forming process that then you have, micro cracks and everything that form in it that would help take into account?
Yes. The example on the aluminum there, that's Alcoa plate. Those iron-bearing particle steel, they crack during the rolling process. So they're there during the rolling process. And then you elongate the grains during the rolling process, and you get the residual stress during the rolling process. But all of that goes directly in the model because you're modeling residual stress, spatially, those cracks spatially, and those elongating grains. So the idea is to be able to capture, something, exactly that. So how that, and then when you form around a corner, how does that turn, and what's the flow? But it does flow, and you can cut them up and look at them. You do, and okay, these are how the grains flow. Well, you want to capture that directly.
Last question.
Yeah, I had a question. First, a quick story. I was at a presentation where they were showing a full 3D CT showing the residual stresses grain by grain throughout a component, right? And the point of that was to show a fracture and the localization of, as you described, right? So the techniques you described were volume averaging techniques, but the things like corrosion is a surface thing, right?
Yes.
The fracture starting is a surface,
Yes.
Generally is a surface thing.
Yes.
Is there an equivalent for this surface averaging, surface statistical method?
Yeah,
versus,
well,
what you
the
showed?
sad thing is we call it a statistical volume element, but most of fatigue is a statistical surface element. Absolutely. Yes, because so unless you're a very high cycle, you got internal crack starting. But no, so the term, even if you're in 2D, that misnomer is used. Yes.
Okay, thank you.
Well, thank
you
you.
very much.